All right, hello everyone. My name is Rajat, and today I'm going to be presenting my research project. I completed this project with my mentor, Arpit Jathapara, and I'm presenting here from the Bay Area. Yeah. In this project, we developed models to enhance melanoma detection, aiming to assist traditional methods by combining diverse techniques, and we achieved high OCROX and accuracies. So in our study, we compared two different models to find the most effective one. And this research demonstrates the potential of ML to revolutionize healthcare practices. Here's a table of contents that I'll be going through. First, an introduction, background information, then the initial CNN we created, then the updated CNN, how we improved the initial CNN, then the logistic regression model we created, and finally, just the conclusion. First, the introduction. So what is melanoma? The image is an example of a malignant melanoma skin lesion. Melanoma is a type of skin cancer that develops in the melanocytes located near the bottom of the epidermis, which is the outermost skin layer. It's caused by exposure to UV radiation, which damages skin cells. Although it's the least common form of skin cancer, it's the most deadly. The rates of melanoma diagnosis have doubled from 1982 to 2011, highlighting the increased prevalence of this disease. In 2024, it's estimated that 100,000 patients will be diagnosed with melanoma. Survival rates significantly vary depending on the stage of diagnosis. Patients diagnosed with stages 0 to 2 melanoma, that just means the cancer is not spread beyond the original site, have a high survival rate of 98.4%. However, with patients diagnosed with stage 3 melanoma, where the cancer has spread to lymph nodes or nearby skin, the survival rate drops to 63.6%. Unfortunately, for patients diagnosed with stage 4 melanoma, where the cancer is spread to other body parts like the spine, the survival rate is 22.5%. This is why early diagnosis is so important. Now I'm going to go over current diagnostic methods. As mentioned, early diagnosis of melanoma is crucial for a patient's survival, and the first step is to do a visual test. Usually doctors do this. If melanoma is suspected, a biopsy will be performed. In the biopsy, a portion of skin is just removed and tested. And based on the results from the biopsy, the doctors will confirm the presence of melanoma and determine its stage. Further testing, such as MRIs or ultrasounds, may be done to assess the extent of the cancer. So recently, AI has been playing a huge role in the medicine field. AI techniques can help in identifying diseases, improving diagnostic capabilities. For example, AI-powered medical imaging detects cardiovascular diseases like atrial enlargement and neurological abnormalities like amyotrophic lateral sclerosis with high accuracies. By leveraging AI, medical professionals can achieve quicker and more precise diagnoses, leading to improved patient outcomes. Additionally, using AI can ease the physician workload, preventing workplace burnout, allowing for more patient care. So AI is going to continue helping the medicine field. And we believe AI could help in melanoma diagnosis. Now I'm going to go over the initial model we created, which was the CNN. So here are some examples of malignant and benign samples of melanoma. Distinguishing between these two can be pretty challenging, as if you look in the image, they're pretty similar, right? So that's why subtle differences in texture, color, and borders have to be carefully analyzed. And we use deep learning to detect these small differences. So the first model we employed was a CNN, a convolutional neural network. Essentially, they just work by processing input images through a series of convolutional and pooling layers, and they extract features, and they use that features to create a prediction. So first, a filter is applied, and that detects initial features, and that generates feature maps, which highlights the presence of patterns in the images. Then pooling layers will reduce the dimensionality while preserving the most important information. And then more passes of these convolutional and pooling layers go through, more complex features are extracted, and spatial dimensions are further reduced. Finally, there will be a fully connected layer after the layers are flattened, and that'll output a prediction, predicting whether it'll have a malignant melanoma or not. Regarding the data set we use for our project to train the model on, in 2020, on Kaggle, SIAM hosted a Kaggle competition, encouraging participants to develop a model for predicting melanoma. So then, after the competition was over, a data scientist enhanced the competition data by adding 40K external images to the existing 30K images and storing them in a TF record format. And these images were also resized to 7 different image sizes, ranging from 128 by 128 pixels to 1024 by 1024 pixels. We used this data set, and my model was initially tested on the 512 by 512 size image pixels. 20% of the data was used for validation, and the remaining 80% was used for training. So before building my model, we extensively reviewed Kaggle notebooks to gather techniques that worked. So we decided to use TensorFlow as the main framework, and we also used TPUs, tensor processing units. These units essentially just enhance the runtime and computational efficiency. For pre-processing, we included data augmentations like a random rotation, random flip, random vertical flip, and random horizontal flip. Additionally, each image was also divided by 255. This just normalized the data, ensuring consistent scaling between all layers. To optimize the learning performance, we also used a cosine learning rate. Essentially, the learning rate was gradually increased to a max and then gradually decreased following the shape of a cosine curve. So in the model, we use Google's EfficientNet B6 architecture. This is just known for its efficiency and effectiveness in image classification. We also use global average pooling to reduce spatial dimensions, and we also added a dense ReLU layer, which introduced nonlinearity, allowing the model to capture more intricate patterns in the data. Then to prevent overfitting, where the model gets used to the training data, we added a dropout layer, which randomly ignored 50% of the units from the previous layers during training. And for a final prediction, we used the fully connected output layer, providing the probability score for the presence of melanoma in the skin lesion images. The model was trained using the binary cross entropy loss function, and this is generally well suited for binary classification tasks. So this image, it just shows different scaling, the width scaling, depth scaling, and resolution scaling. So when you scale CNNs, you want to use all 3 of them, which is compound scaling. And EfficientNet B6, created by Google, it essentially does this really well, which is why we chose to use it. In evaluating the model's performance, we use 2 metrics, accuracy and aux. Accuracy is just a proportion of correctly classified images, and it's a commonly used metric. However, it can be misleading, especially in datasets with imbalanced classes. If there's a large amount of one class, like 90% or more, a model can get all of that right and everything else wrong, and it'll still get an accuracy of 90%. However, awk, on the other hand, measures the area under the receiver operating characteristic curve, and that just plots the true positive rate against the false positive rate. Awk values closer to 1 indicate a better performing model, as it suggests that model has a high true positive rate and a low false positive rate, which is what we want. So after 15 epochs of training, the model achieved the performance shown above, which is overall pretty good. But we still decided to further enhance the model's capability. So we added some updates to the CNN. So the first update we did were increased data augmentations. So a random brightness adjustment, a random contrast adjustment, a random saturation adjustment, which is just color intensity, and a random hue adjustment, which is just color tone. These augmentations achieved a training accuracy of 0.946 and a training awk of 0.936, and the validation accuracy was 0.944 and a validation awk of 0.944. The performance was slightly worse. However, we decided to keep these augmentations as they made the model more robust, because not all images will be taken the same way. So that's why we want to include more augmentations to expose the model to different types of images. So to optimize the model learning process, we also included various learning rates. Here are all the learning rates, custom learning rates we tested with ramp-up epochs, so the number of epochs it takes to reach a full learning rate, and a decay rate, so how fast the model's learning rate will decay. So among these configurations, the model performed best with the gradual warm-up, 4 epochs, and a moderate decay of 0.85. And yeah, as you can see, the performance is pretty well, higher than the last slides. Then we tested our model on different image sizes. We kept everything the same. We just changed the input image dimensions for the CNN. So generally, the model's best epoch was around 9 to 12, which is normal for CNNs, as models start to overfit after that. So the model after that will get too used to the training data, and it'll perform badly in other data. And overall, accuracy consistently performed better than awk for every single image size. This is likely because the dataset we used was imbalanced. It had a large amount of non-malignant lesions and a small amount of malignant lesions. And furthermore, the 512 by 512 image dataset that actually performed the best. This could be because the image size was large enough to provide adequate features that the CNN could extract, while also being not so big such that it introduces a lot of noise in the model's generalization ability and confuses it. Next, we create a logistic regression model. So a logistic regression model is just a binary classification model and essentially uses inputs and maps them to create a linear combination and outputs a probability regarding whether it'll contain the said class or not. For example, as you can see, these inputs go in and then it'll output two options, happy or sad. But in my case, the two options would be malignant melanoma or non-malignant melanoma. The data set we used for this did not come with, the test set did not come with diagnoses. It was just values to be tested. So because of this, we just split the training data into 20% testing and 80% training. And in the data set, we looked at sex, age, and anatomical site for data prediction. So in pre-processing the data, we hot label encoded categorical variables into a numerical format because logistic regression requires numerical input. For example, sex, like male or female, will be converted into zeros and ones, and site would be converted from zeros to sevens, as there are 8 possible sites. After encoding the categorical data, we use the logistic regression model from scikit-learn to solve it. The logistic regression model achieved an accuracy of 0.90 and an awk of 0.76. The awk indicates that the model struggled with correctly classifying malignant samples, just as the CNN, likely again due to the imbalance in the dataset. Conclusion. So in conclusion, we developed 2 models for diagnosing malignant melanoma, a convolutional neural network and a logistic regression model. The CNN performs significantly better than the logistic regression model, likely because it could extract more complex features, and also because the logistic regression model was trained only on a few data, only breed data, and couldn't really provide a strong indication based on that data, which is not directly related to the image in any way. It's just data about the patient. However, both models did face challenges with the awk metric, and this again is due to the data set's imbalance between malignant and benign samples. So more images of malignant samples for each model to be trained on could mitigate this issue. All right, thank you for listening, and any questions?
Thank you so much. Yeah, I actually do have a question on that last point that you mentioned around awk. So you're saying that a lot of the issue came from the class imbalance in the underlying data set. How mechanically, how would you kind of change that? Is it just in terms of the I'm curious like what someone would do to
Yeah, sure.
improve the data set or refine it so that it
Got it. Yeah, so the data set we use actually, it just contained almost a lot of the data was just non-malignant, just regular skin lesions. Only a small amount of the data was actually malignant lesions. So we would have to just find more images of malignant samples online or somewhere, and then train the model on those images. So that would improve its ability to capture and detect the malignant images a bit better.
makes sense. So would it be ideal to have something closer to 50-50, or is it like what's an ideal ratio in your mind?
Yeah, I guess 50-50 would be a good ratio. Maybe honestly, probably even if more malignant samples could be used, that would be better because we want to diagnose the malignant samples, but we also want to reduce false positive rates and false and true negatives.
That makes sense. Very interesting. A couple other things that you mentioned in your presentation that were interesting. So you had mentioned that like the diagnosis for melanoma had doubled or increased like pretty significantly over, like, do you have a sense of why that is?
I'm not fully sure. Maybe it could just be poor diet or because the cause of melanoma is exposure to sunlight, right? But like cancer can be increased by many factors. It could just be like poor health as time goes on.
Got it. And then final question. I'm curious, future applications or future direction for your research. Are you going to do additional models or I'm curious the next steps?
Yeah, I guess next step would be trying different models to predict the melanoma, trying different base CNN models, maybe creating my own model architecture to instead of using Google's EfficientNet for the base architecture and trying different CNNs and different models for the tabular data too.
Perfect. Thank you so much.
Yep.